What's up, everybody? It's Rudy here. Hope you all having a great day. This one goes out to my Algebra II students or anybody else who wants to learn. And today our topic of discussion is quadratics. We're going to start chapter 4. The entire chapter is about quadratics. And we're going to kind of go step by step, try to help you figure out what exactly is a quadratic and why do we care about them, and then I'll try to show you in each lesson how to both graph a quadratic and solve a quadratic formula or quadratic function with the quadratic formula. So let's talk about quadratics. How about it, right? Okay, so one of the first things that I constantly hear people say is, hey Rudy, is this hard? It's a little maybe tougher than what we've talked about before, but I think if you follow my steps and follow what I'm going to show you up here, it's not too bad. This will be the first part of another two-part video on quadratics, because I won't be able to get through this entire first section in one video. If you're going to follow along with me, this is Chapter 4, Section 1, or Chapter 4, Lesson 1, I should say, and it is posted on the Google Classroom page, so make sure that you pull that up when you're watching this video so you have something to go along with, because that's what I'll be going along with in this explanation. Okay? So, what the heck is a quadratic? Now, if you all remember, if any of you were in my class the first semester when we talked about parent functions, remember, we talked about 4 parent functions. We talked about a constant function, which is y equals any number. We talked about the identity, or a linear function, which was y equals x. We talked about an absolute value function, which is y equals the absolute value of x. And that fourth one we talked about was quadratics. It's y equals x squared. Now that's the simplest version of a quadratic you can possibly get, y equals x squared. What I'm going to show you right now, though, is standard form of a quadratic equation. You may also see the parent function or an equation written like this, f of x equals x squared. Keep in mind, this really is the same thing. This is written like an equation. This is in function notation. F of x and y, they mean the same thing. This one is just telling you, yeah, it's a function, where this one is not really telling you it's a function. You'd have to figure that out. All right, so if you see me write either y or f of x, you know, it's the same thing. I'm doing the same thing, right? So this right here, these two are really what we're going to focus on in this chapter. That is the basis of a quadratic equation or a quadratic function, right? So let me dig a little deeper into that. So I just said, and if you're looking at the lesson, the printout that I've given you, one of the very first things it talks about is standard form of a quadratic equation. Like I said, this is the parent function, f of x equals x squared. It's the most simplest, basic form of a quadratic equation you can get, but it's not standard form. Here's standard form. It's f of x equals ax squared plus bx plus c. Okay? Well, what the heck does all that mean? I just threw a bunch of letters up there, but I didn't really explain much. Well, here's that x squared that I was mentioning earlier in the parent function. A, B, and C, those are just numbers. Okay? Now, in order for it to be an actual quadratic function, A here, the very first number, or what we would call the leading coefficient, and I'll even write that up here. That's your leading coefficient. Whatever number's out front. In order for it to be a quadratic function, your leading coefficient, a, cannot equal 0. That's it. It's got to be some other number. It can be any number. It can be rational, irrational. It can be positive. It could be negative. It doesn't really matter. It just cannot be 0, because if it was 0, this would become 0, and you don't have a quadratic anymore. You either have a linear term or a constant term. Okay? So that's a big one right there for a quadratic equation. But anyway, what we're seeing here is you have a number times x squared plus a number times x plus another number, or a constant. Now, if these two terms are not here, that's fine. You can still have a quadratic equation with just the first term. You don't need these two terms. But if you have all three terms, this is the order in which it should go. X squared term first, followed by your x term, followed by your constant. Let me show you with an actual equation what I mean, or an actual function. So let's say we have, I don't know, f of x equals negative 3x squared plus 6x minus 10. That would be an actual quadratic equation, or a quadratic function. In this case, if you look here, negative 3 is out in front of x squared. So negative 3 is a. A is negative 3 in this case. B would be 6, because 6 is the coefficient, or 6 is out in front of x. So B would be 6. And finally, whatever number's here at the end, in this case minus 10, or your number by itself, C would be negative 10. So if we're looking back here into standard form, ax squared plus bx plus c, we can see ax squared plus bx plus c. And these can be positive or negative. It doesn't matter. Okay? So that's the basis of what a quadratic is. And so what does that mean? On a graph, what does that mean for us in the real world? Let's think about that for a second. Up to this point in Algebra II, especially if you were in my class for the first semester, mainly what we talked about was lines, linear equations and linear functions. And what that means is when you graph it, it's constant. And it's the rate of change is either gradually up or down, can be flat, can be perfectly vertical. But the difference is it gives you a line. A quadratic, on the other hand, it gives you something else when you graph it. Let me draw just a quick illustration of what I'm talking about. But a quadratic, when we graph it, it does not give us a line. Instead, it gives us a curve. So if you recall back when we talked about, or when we graphed the parent functions, I'm going to put two up here. I'm going to put f of x equals x squared and f of x equals negative x squared. So if I take those and toss them up on a graph, let me show you what we get. And then I'll explain why do we care about this. So I'm just going to draw a quick y and x axes. Real quick. Nothing crazy. Alright. Here's my f of x, or my y-axis. Here's my x. Alright. So if I took f of x equals x squared and I graphed it, I'm just going to get a graph that kind of looks like this. And I'm just going to sketch it. I'm not going to really go crazy with it. Right? That would be f of x equals x squared. The shape that we got there, that's a curve, right? It looks like a U. It's like a U-shaped curve. Another name for it, though, if you've never heard this before, this is known as a parabola. Right? So it's the shape is of a parabola. Or we can call it, like, if we're using a different tense of it, we can say it's parabolic. You know, if we're using it as an adjective. As a noun, it's a parabola, or it has a parabolic shape. Okay? U-shaped. If I took this one, f of x equals negative x squared, and I graphed it, that just flips it upside down. And it would look something like this. Here, I'll use a different color, just so we can distinguish the two. So it would look something like this. Okay? So that's f of x equals x squared, f of x equals negative x squared. But this is what we're talking about. So once again, why do we care about this? Well, if you look at this shape, right? The shape of this arch or this parabola, I want you to think about what are some real life applications that you see a shape like this. I can think of a few. Any of those people out there who are thinking about maybe joining the military someday, Army, Marines, Navy, any of that kind of stuff. We know what goes up must come down, right? That's the way gravity works in the real world. Well, when we talk about gravity, something coming up and getting pulled back down, we're really thinking about a quadratic. And so I mentioned the military, right? Let's say, I don't know, let me do a little quick illustration here. This is the ground, right? And you've got a wall here, or some kind of structure, right? And you've got bad guys over here. Bad, right? And you've got good guys over here. Okay, you got bad guys over there, you got good guys over here, and you got a wall, right? And you're trying to get over this wall. Hi, sweetie. Just stay over there, okay? Okay, I'm teaching my students about quadratics. Just hang out over there, okay? They're on the video. Just, you're good. All right, so anyway, let's say I want to attack this guy over here. It's my daughter. But I can't shoot through the wall, right? You can shoot what is called a mortar. If anybody's ever been in the military or know anybody, there's mortar teams and there's mortars, and that's kind of like a rocket, and it goes up, and ideally you want it to go up and hit the bad guy on the other side. Well, in order to calculate how far they are, how long it will take, trajectory, initial velocities, all that kind of stuff, you need to use what is called a quadratic equation to get that over there. Okay, so that's just one of many uses. I'll give you another idea. And this is a great idea. If we're talking about physics and stress loads, like how much stress can something take, one really well-known thing throughout history that let's go way back to the Roman era. And Romans, they designed something thousands of years ago to help move water from one location to the other, and they used a design like this. I'll try to draw it the best I can. If you're not familiar with it, they're called aqueducts. And aqueducts, if you'd ever seen one, kind of look like this. It almost looked kind of like a bridge with all these arches underneath it, right? And the idea was that you have all these arches, and then you've got this water that flows using gravity downward. Well, in order to hold water up like that, you got to be able to support a lot of weight. Each one of these arches is basically like a parabola in itself. All the downward pressure, if it just went straight down like this, on a flat surface, it would want to buckle, right? But arches like this are better at distributing weight. They distribute weight from all different directions, and then they spread it down the arch, okay? So you've got all sorts of stuff going on there. Well, you can calculate how much stress and how much weight one of these arches can hold, and part of that calculation is a quadratic equation. Now, there's a whole lot more going into this. I just really oversimplified everything. But the bottom line is that it is a quadratic equation is an integral part of how people would, or how Romans, now maybe Romans didn't use quadratic equations back then, but it is an integral part of nowadays how an engineer would possibly figure out how much weight or how much stress can this curved structure hold before it would break or before it's no longer safe. There's a lot of things. Bridges, roller coasters, I could keep going. There's a lot of places where you see curved structures as opposed to linear structures or straight lines, because the curved structure is better at holding that kind of weight or those kind of stress loads. All right, now that I've thoroughly confused you, because I'm sure everybody understood everything that I just explained, right? You can shoot me hate mail if you want to. You all have seen my contact info. Look down in the description if you want to. I'll post it down there as well. I'll keep posting on Facebook. But you can send me terrible notes and letters of how much you hate me right now because I'm teaching you all this. It's all right. It won't hurt my feelings. Okay. Bottom line is, how does all this work? Let's get to the actual meat of the subject. So, if you're with me, let me look here. I am on page, oh crap, where is it at? I am on middle of page 219. Middle of page 219, and I'm on example 1. And let's see, how many examples am I dealing with here in this section? Example 1, we got examples 2, 3, 4. We got 4 examples. So what I'd like to do is, I'd like to knock out the 2 first examples on this video, and then we'll save examples 3 and 4 for the second part. So middle of page 219, let's look at example 1, okay? Middle of page 219, example 1. It says we need to graph a quadratic function using a table. Graphing a quadratic function using a table of values. So example 1, we have, it says graph f of x equals 3x squared minus 12x plus 6. Okay? And we're just going to make a table of values. If you've ever seen this before, table of values is pretty easy. The problem with it, it's time consuming, so I'm going to show you easier, shorter methods, but this is the first one I want to show you. So whenever we make a table of value, you start with your x column, then the function itself, so 3x squared minus 12x plus 6. Then you have your y, or your f of x column, and then you have your coordinate itself, x, f of x. Okay, so you're going to have, ideally you have 4 columns if you're trying to do a really nice table. Remember, your x value is your independent variable. We can pick whatever numbers we want to. I would recommend something hovering around 0. Don't pick numbers that are too crazy. In this case, I'm just going to pick 0, 1, 2, 3, and oh heck, we'll do 5 values, 4. 0, 1, 2, 3, and 4. Once again, I can pick whatever numbers I want to. It does not have to be. You don't have to pick the same 5 I did. I just think that picking things around 0 is the smartest way to start off. I could have done like -1, -2, and so on. What are we going to do from here? Well, we're going to take each one of these one at a time, and we're going to plug them into our formula, or our equation. So we have 3x squared, or 3 times 0 squared, minus 12 times 0 plus 6. And I'm going to rinse and repeat. I'm going to do this over and over and over again. So 3 times 1 squared minus 12 times 1 plus 6. 3 times 2 squared. Notice, each time I'm replacing x with that number from the x column. Minus 12 times 2 plus 6. 3 times 3 squared minus 12 times 3 plus 6. And 3 times 4 squared minus 12 times 4 plus 6. Make sure I did all that right. It looks good. Oh, forgot my squared here. Don't want to do that. Okay. Now we're going to just simplify each one, get ourselves a final number. So 0 squared is 0, times 3 is 0, 12 times 0 is 0. All this zeros out, and we're just left with 6. So we have 6, so my coordinate is 0, 6. And let's keep going. 1 squared is 1. 1 times 3 is 3. 12 times 1 is 12, so 3 minus 12 is negative 9. Negative 9 plus 6 is negative 3. So my coordinate will be 1, negative 3. And keep in mind, I'm doing all this in my head, but if you're more comfortable punching into a calculator, I don't have a problem with that. Just make sure you're actually punching it in exactly as it's written, because if you miss any of these parentheses or any of these signs, you're going to get a totally different answer. You don't want that. Let's keep going. 2 squared is 4. 4 times 3 is 12. 12 times 2 is 24, so 12 minus 24 is negative 12. Negative 12 plus 6 is negative 6. 2, negative 6 is our coordinate. Okay. Keep going. 3 squared is 9. 9 times 3 is 27. 27, we have 12 times 3 here is 36. So 27 minus 36 is what? Negative 11. And negative 11, wait a minute, did I do that right in my head? Hold on, Rudy. 3 squared is 9. 9 times 3 is 27. 27 minus 36. Okay, I'm blanking. No, it wouldn't be that. Okay, no, it'd be negative 3. Yes, negative 9. Yeah, negative 9 plus 6, sorry everybody, is negative 3. I'm not thinking properly. All right, negative 3, okay, and we have 3, negative 3, sorry. And then, lastly, 4 squared is 16. 16 times 3 is what? 48. 12 times 4 is also 48. So 48 minus 48 is 0, plus 6 is 6. And we have 4, 6. Sorry. Okay. So we have 1, 2, 3, 4, 5 coordinates. Those are just going to go on a normal graph, right? We're going to graph them. So let me break out my green here. I'm going to put the graph right here. Yeah, that'll work. I'm going to put the graph right here. So, X and Y axis. Let's go ahead and draw those. Make sure you're all using a straight edge, by the way. When you're drawing this stuff, use a straight edge whenever you can. It just looks better, and it's a good practice to get into. So there's my Y, or my f of x axis. Then we have my x-axis right here. So f of x is up here. X is right here. And I'm just going to plot these points like I normally would, like any coordinates. So 0, 6, neither left nor right, but up 6. So 1, 2, 3, 4, 5, 6. 1, negative 3, so forward 1, down 3. Forward 1, down 1, 2, 3. 2, negative 6, so forward 2, down 6. So forward 2, down 1, 2, 3, 4, 5, 6. Right there. 3, negative 3, so forward 3, down 3. And lastly, 4, 6, so forward 4, up 6. I know you were all in kindergarten once. You remember connect the dots. We're going to connect some dots here. But the easiest way to do this, I always tell people when drawing a parabola, when trying to connect your dots to form your quadratic, the graph of your quadratic equation, I don't like to do one whole curve from top to bottom, then back up top, I think you make a weird curve. I actually start down here at the lowest point, which is the vertex, and I do like a half curve up each side. Kind of watch how I do it. You all can do it the way you want to, but I think this is the easiest way. So I'm going to start down here, and see, I just did a half curve, right? And then I'm going to start here on the other side, and I'm going to do another half curve. And I just think you get better looking parabolas that way. That's just my opinion, okay? But there's our graph. So that's it. That's this equation up here, 3x squared minus 12x plus 6 on the graph. And you can also toss it in any graphing calculator. I wish I was with you right now. I would show you. Maybe I'll break out a projector in another video and show you how to throw it up on a graphing calculator. But there you have it. Okay? All right. I'm going to do one more of these real quick for example 1, and I'm actually thinking I'm going to probably toss example 2 on the second video as well, because this one's running a little long, and I'm sure half you've probably fallen asleep, and I hope the sound of your head hitting the desk hasn't woken you up yet. Okay, so let's go ahead and look at one more of these, how to do it, and if you're with me, I'm at the bottom of page 219. Bottom of page 219. I'm going to just erase this without erasing the entire table. And I'm seeing two problems at the bottom of page 219, 1A and 1B. Let's see. Let me figure out which one I want to use. Oh, wake up, computer. Computer wants to fall asleep on me. All right, and my mistake. All right. Let's see. You know what? Let's go with 1A at the bottom of page 219. So if you're following along with me, bottom of page 219, Guide to Practice 1A, it says g of x, not f of x. So let's swap that out with a g. And, oh, we can't have u here. That's our old function, so let's get rid of that. And let's get rid of the f here, because it's g of x. Probably would have just been easier to draw a whole new table. Oh, well. So we've got g of x here, g of x here, and g of x in this case is negative 2x squared plus 8x minus 3. And the reason I chose this one over the other one, because if you look at the bottom of page 219, there's two different problems down there. The reason I chose this one, it's got a leading coefficient with a negative value. And I know you all just love negative numbers, right? Makes your life a whole lot easier. So why not go with something that you love? All right, so I'm going to punch that in here. We got negative 2x squared plus 8x minus 3. Once again, we're going to take each x value. I'm just going to pick the same 5 that I used in the previous example. These are 5 good values to work with. It's no big problem. Let's see what we get when I use them. So I'm going to plug all 5 of them into my function here, or my equation, and see what I get. So we have negative 2 times 0 squared plus 8 times 0 minus 3. Negative 2 times 1 squared plus 8 times 1 minus 3. Negative 2 times 2 squared plus 8 times 2 minus 3. Negative 2 times 3 squared plus 8 times 3 minus 3. And last, negative 2 times 4 squared plus 8 times 4 minus 3. So like I said, it's the same thing over and over and over again. It's like rinse and repeat, shampoo instructions. All right. This is going to give us 0. This is going to give us 0 because anything times 0 is 0. So we get negative 3 as our y, or a g of x value. 1 squared is 1. 1 times negative 2 is negative 2. 8 times 1 is 8. So negative 2 plus 8 is 5. 5 minus 3 is 2. we can put our coordinate over here if we want. So 0, -3, 1, 2. Let's keep going. 2 squared is 4. 4 times -2 is -8. 8 times 2 is 16, so -8 plus 16 is +8. +8 minus 3 is 5. So 2, 5 is our coordinate. 3 squared is 9. 9 times -2 is -18. 8 times 3 is 24, so that's -18 plus 24 is 6. 6 minus 3 is 3. Yeah, am I doing this right? Sorry guys, I'm doing this all in my head. 3, 3. And lastly, 4 squared is 16. 16 times -2 is -32. Plus 8 times 4 is 32, so -32 plus 32 is 0, minus 3 is -3. And I'm going to double check some math real quick because I think I did one of these too quickly in my head. Let's see, 1 squared is 2, 2 plus 8 is 6. Yeah, I did that. There we go. I knew one of these had to be wrong. 1 squared is 1. 1 times -2 is -2 plus 8 is 6. 6 minus 3 is 3. Sorry about that, people. All right, so we've got our coordinates. 0, -3, 1, 3, 2, 5, 3, 3, and 4, -3. And we are ready to graph this. So, we'll switch to black for this one. I like to switch colors frequently just because if you use one color, it just turns into a big mess and shows no distinction between different steps, and that makes it even worse for you guys. So, let's check this out. Draw my axes. G of x is up here. X is down here. Plot my points. 0, -3, so neither left nor right, but down 3. 1, 2, 3. 1, 3, so forward 1, up 3. 2, 5, forward 2, up 5. 3, 3, so forward 3, up 3. And 4, -3, so forward 4, down 3. And once again, we have our connect the dots. Something like that. That's a little low there. Make it look pretty. There we go. As Bob Ross would say, happy little parabola right there. So we have all of our work, and then we have our graph of our parabola, and then that's how you graph a quadratic equation. So just to summarize, that was example 1. Quadratics, we're talking about curves. We're talking about something with an x squared term in it, and we're going to continue to chip away at this in the second part of this video, and we will go on to page 220 in chapter 4, lesson 1, and we'll start with example 2. I would recommend, if you just want to take it a little bit at a time, feel free to start the actual assignment. It's posted on Google Classroom. And I think the first 3 or 4 problems that I have assigned to you, and I can look real quick what I've got here. The first 3 or 4 problems would be, if you skip down to the actual assignment on page 224, 13, 15, and 17, you should be able to take a look at it if you want to. But like I said, you don't have to. You can wait till you see the second part of the video. Give it a try. Look into it a little bit more. Get a hold of me if you want to. You can call me. I posted the new phone number on the Facebook page, Messenger, Google Hangouts, Skype, email. Get a hold of me. Let me know what you're thinking, and I will start with part 2 shortly. Okay? Thanks, everybody. Have a great day.